So now we have an example of a problem where we're going to do pressure work. So here the question asks us, a gas contained within a piston cylinder assembly expands in a constant pressure process at 4 bars from one volume of 0.15 meters cubed to a final volume of 0.36 meters cubed. Calculate the work in kilojoules. So here we need to know pressure as a function of volume. But it tells us here that the piston cylinder assembly expands in a constant pressure process. So the pressure is always 4 bars. Now remember that a bar is almost an atmosphere, but an atmospheric pressure is usually 101.3 kilopascals. And because it's metric, we don't really like that unit because it's not a kind of a round number. So bars are 100 kilopascals. So a bar is almost an atmosphere, but it's in a kind of a nice round denomination. So our known information in this problem is that we have a constant pressure process. So P is equal to constant. And we know that that constant is 4 bars. A volume 1 is 0.15 meters cubed. And volume 2 is 0.36 meters cubed. We're required to find the work in kilojoules. So I want to try to draw a schematic. So my schematic might look like this, right? This is just the same schematic we did before. We're going from V1 to V2, and I have a system here where somehow this pressure is being kept constant. So if I was drawing this out, then I would say as I move from my initial volume, which is 0.15, to my final volume, which is 0.36, then I have constant pressure. So sometimes it's helpful to draw things out on a PV diagram, because remember that integral that we're going to do, the integral of P dV, is just the area under this curve. So I can do some calculus here, and we'll do that. But if you prefer to solve these kind of problems geometrically, you can do that, at least in some cases, because the area under this curve is going to give us our work. So here we're going to try to state and justify our assumptions. So here we're told that the pressure is constant. We're going to assume that, that this system is close to frictionless, or at least that the work that we're losing by friction as our piston moves through our cylinder is really small compared to the total work done. So we're going to say that it's equal to 0, but really the implication here is we can neglect it, which means that it's quite small compared to the other terms that we're going to be talking about. We're also going to assume that this system is a closed system. And the reason that we have to assume this is that if it's an open system and mass is coming in and out of our system, then we have to use a different version of the first law. So in this class, up until about the first exam, we're going to only be talking about closed systems. So we're going to talk with the first law, the version that we're talking about in this class. So now we're going to try to calculate the work here. So we remember our governing equations, in particular, that work as we move from our initial to our final state is equal to the integral of P dV. Now we're working in metric units here, so I just want to make sure that my equation makes sense, that there's no kind of conversion factors that I need to put in here. So if I turn my pressure into pascals, which is newtons per meter squared, and I multiply my volume, which is meters cubed, then I would get an answer in Newton meters or joules. So let's try this. So work is the integral of P dV. I know that the pressure is constant. And because it's constant, I can take it right out of the integral here. So the P comes out, and I get that work is equal to pressure, which is a constant, times the integral of dV. This is my second favorite kind of calculus. The best math is when the answer is 0, but the second best kind of math is when we're doing calculus of a constant like this, because then this integral of dV is just delta V. And we take the final volume minus the initial volume. So now we have an equation and we know all the information. So I can put my pressure in here as 4 bar, multiplied by the change in volume, and my volume is given in cubic meters. Notice that I'm keeping the units in all of my calculations here because I want to make sure that I don't mess up the units and get some kind of answer that doesn't look very physical. So here I see that I have 4 bar multiplied by 0.21 cubic meters. Now bar, this doesn't really make sense. Bar times meters cubed, I don't know what that is. So I'm going to turn bar into pascals. So I know that 1 bar is equal to 10 to the power of 5 pascals. Or if I wanted, I could say 100 kilopascals here. But I'm going to go right to pascals, or newtons per meter squared. My bars here cancel out. So this is how I always remember how to do this fraction when I'm doing unit conversion. I want to get rid of the bar here in the numerator. So I got to put the bars in the denominator over here, which means that my pascals has to go on top. Now here, if I take my cubic meters and divide by meters squared, then I'm left with just meters. So now I have 84,000 Newton meters. I know that 84,000 Newton meters is 84,000 joules, because again, I can do sort of this simple unit conversion here that 1 joule is equal to 1 Newton meter. So here, my Newton meters cancels out, and I get 84,000 joules. But the problem wanted my answer not in joules, but in kilojoules. Right? I guess here, so I canceled out these Newton meters. Right? So I want an answer in kilojoules here. So I know, again, I want to get rid of this term of joules. So I put the joules term on the bottom. So there's 1,000 joules here, and I put kilojoules in the numerator. Now the joules cancel out. I divide by 1,000, and I get 84 kilojoules. Now the last part of our solution method is that we're going to validate what we're doing. So let's check the units. That's something that we can always do, even if we don't have some kind of physical understanding of the problem. So we checked the units through all of our calculations, and we got units that we were expecting. We were looking to get work, and we got work. So the units we got were in kilojoules, which is what we were expecting. The final solution also gave a positive value. So I know that hip to win tells me that work in is negative. But this is work out, right? Because the system is expanding. It's pushing our system, which is the air inside of our cylinder. It's pushing that cylinder out. So the system is doing work on the surroundings. If work in is negative, then work out is positive, and we got a positive value here. So if we do the integral correctly and we go from the initial time to the final time, you should always get the sign right. But it's always good to check this, right? So we did get the right units and we got the right sign because the air in our system is doing work on the surroundings. So here I don't particularly have an intuition for what the magnitude of the work would be done here. I'm not familiar enough with these piston type problems to say like, oh yeah, that makes sense that that'd be 84 kilojoules. But I do know that the unit analysis made sense, and I know that the sign of my answer was correct. So I can't tell you that 84 kilojoules is the right answer, but I also can't prove to you that it's wrong. And if I got a unit that didn't make sense as energy, or I got the sign wrong, then I would be able to notice this right now. And that's sort of the benefit of checking like this at the end of a problem.